In this video, I will discuss the basics of Anova and include an example using SPSS. First of all, the purpose of doing Anova is to compare 3 or more means, or to compare 3 or more groups. So our null hypothesis when doing Anova is null hypothesis all the means are equal versus the alternative that at least one mean is different. I always like to think of this as the Sesame Street alternative, because when I was a kid there was a segment on the show where they broke the screen up and they always sang that song, "One of these things is not like the other." So if I think of it that way, I never forget how to do the alternative hypothesis. Anova stands for Analysis of Variance. It basically compares the variation within the samples to the variation between the samples. So if you look at these two sets of box plots here, in the ones on the left, they all have tall boxes, which shows that there's a lot of variation among individuals within each group. With this much variation among the individuals, it would not be surprising if another set of samples gave quite different sample means. So the observed differences could easily happen just due to chance. Now if we look at the boxes on the right side, they have the same centers as the ones on the left, but the boxes themselves are much shorter, meaning that there's much less variation among individuals in the same group. So it's unlikely that any sample from the first group would have a mean as small as a sample from the third group. So because the means are far apart and the variation within the group is small, then it's more indicative of a real difference among the means of the three populations. So Anova, what that's going to do is it's going to compare these. It's going to look at how much variation within the group and compare that to how different the different means are between the groups. There are two basic requirements for doing analysis of variance. First, the data for each group needs to be normally distributed. We can check this by doing a QQ plot of each sample. And if there's not any obvious departures from normality, we can feel pretty good about the normality assumption. The second condition is that the populations have to have the same variation. Now, obviously, we're not going to know what the population variance is, so our rule of thumb is to look at the sample variances, and if the largest sample variance is less than 4 times the smallest sample variance, then we're going to conclude that it's reasonable to assume that the population variances are the same. All right, so let's look at an example. An experiment was conducted to see what color attracts insects the best. 6 boards, each of 4 colors, were placed randomly in oat fields. The boards were covered with a sticky material, thus trapping insects that came in contact with the boards. The number of insects trapped on each board was recorded. So we were comparing 4 groups here, basically the 4 different colors of boards: blue, yellow, white, and green. And we want to know, are the mean number of beetles for each of these trapped on each of these boards, if they're different. So null hypothesis is that the mean for the blue board is equal to the mean for the yellow board, is equal to the mean for the white board, is equal to the mean for the green board, or in other words, all the means are equal, versus the alternative hypothesis that at least one of those means are different. One of those things is not like the other. First thing we need to do is check the requirements. So I started here in SPSS. Here is all my data. You can see that the board color is in the first column and the number of beetles trapped on each of those boards is in the second column. So first thing I want to do is a QQ plot. So I'm going to go to the Analyze menu, down to Descriptive Statistics, and I'm going to choose Explore. Once in Explore, then for my dependent list, this is my output. Okay, so here's where I'm going to put the number of beetles, and on my factor list, this is where I'm going to put the board color, because this is going to do a separate QQ plot for each board color. So next, I'm going to click on that Plots button over there so I can tell it that I want it to do those QQ plots. So in this menu, you need to check mark the box that says Normality Plots with Tests. then you can hit continue, and here's the 4 different QQ plots that I got from that. So it did a separate QQ plot for each board color. And looking at these, there's no like really obvious rainbow looking thing or anything on those, so we don't have to be too concerned about any departures from normality. We can go ahead with the assumption that they're normally distributed. Along with QQ plots, when you do that explore, it's also going to give you a box plot of the data. So this is going to give us a good look at the data, and just from looking at my box plots, to me it looks like, yeah, definitely, I think we're going to see a difference in the board colors. Also, along with that explore function, we get all this fabulous information about each of the different groups. And the one that I want to pay most close attention to is the variances, because I'm going to use those numbers to check my second requirement, that the variances are the same. So I made my own little table using those variances for each of the 4 different colors. Now remember, our rule of thumb says that if I look at the largest and the smallest variance in the group, I take 4 times the smallest. That should be bigger than the largest. So in this case, my smallest was that 14.167. If I multiply that by 4, we get 56.668. That is larger than the largest variance in the table, which was 45.067, which means that we meet the requirement. So we've checked the requirements. Now we're almost ready to start analyzing the data. Just like when we were dealing with the independent 2-sample t-test, in SPSS we have to do the kind of little quirky thing where we have to recode our variables. So SPSS would really rather have everything as numbers instead of blue, green, white, yellow. So in SPSS, I'm going to go to the transform menu and I'm going to choose automatic recode. Once in that dialog box, I am going to put my board color over for my variable name. That's the one I'm trying to recode. I'm going to give that a new name. I'm going to call it color code, and then I'll click on add new name, and that'll put it back up there at the top. Then I'll click on OK, and back in my worksheet I can see that I have this new variable called color code, and it's just given a 1, 2, 3, 4 to each of those 4 colors. So now I'm all set to start doing my analysis of variance. Now I go to the Analyze menu, choose Compare Means, and I'm going to select one-way Anova. Once in there, I'm going to tell it what I was measuring. That's the dependence list. So the thing we were measuring was the beetles. And the factor is the color code. Okay, so your response variable goes up in the dependent list, and your grouping variable, in this case the color code, goes down here in the factor list. Then I'm going to click on the options button here, mostly because just the standard output that they give you in SPSS isn't a lot. So if I click on the options button, I can get SPSS to tell me a few more interesting things. So once in the options button, I'm going to click on the Descriptive Statistics box and also the Means Plot box, just to give me a little bit more output. All right, so here's what the output looks like in SPSS. So first of all, we can see the degrees of freedom for our analysis of variance. Now, something that's a little bit different about Anova versus doing the t-test that we did in previous lessons is that there's not one number for degrees of freedom in Anova, there's 2 numbers for degrees of freedom. We're going to have a between groups degree of freedom and a within groups degree of freedom. So both of those numbers are reported. So in this case, we have 3 and 20 degrees of freedom. We also have our test statistic. The type of test statistic we have is an F statistic. In this case, its value is 44.464. And we'll also get our p-value, which SPSS calls that sig, of 0.000. Now, another thing that's a little bit different from the 2-sample test that we've looked at earlier, or even the 1-sample test, is that there's no one-tailed versus two-tailed when we're dealing with ANOVA. There's just, in fact, it's called like a multi-tailed test, really, if you want to get technical. But so it's just one number. You don't have to worry about one-tailed or two-tailed. In addition, since we told it to do those descriptive statistics, then it gives us all this extra information up here. So for each sample, for each color, it's going to give us the mean, the standard deviation, and it's going to give us 95% confidence interval for the mean, the minimum, the maximum, standard error. So it gives a lot of interesting information up there. All right, so back to our hypotheses. Null hypothesis was that all the means were equal. The alternative was that at least one mean was different. Our p-value was 0.000, and we know that if p is low, HO must go. So we're going to reject the null hypothesis. This means that we have sufficient evidence that at least one mean is different. Looking at the means plot, that was the other box that we checked when we were doing the options for the one-way ANOVA, can give us a little bit of an idea of where those differences are. So looking at this, you can see, hey, blue and white seem to be pretty similar to each other in color. Green seems to attract a few more bugs, and yellow up here seems to attract the most bugs of all. There's another plot that you can do that's even more helpful, I think. I like it the best to look at. If you go under the Graphs menu, you're going to choose the Legacy Dialogues, and then you're going to choose the Error Bar Graph. And what this one's actually going to do is it's going to do a graph of the confidence intervals. So here in the dialog box, the default is simple. You're going to stick with that. So you're just going to click on Define when you get to this step. Then the variable that we're looking at, this is the thing that we're measuring, so that's going to be our beetles. And the category, again, that's the grouping variable, so that's going to be our board color. So once I do that, this is what the error bar plot looks like. And all it's doing is it's graphing each of those confidence intervals. So kind of give you an idea of what it's doing here. Here's the information that we got from the descriptives. And if you look at this first one here for blue, the confidence interval went from 9.2243 to 20.4423. So this graph is basically just trying to make a graph of the 4 different confidence intervals that we have here. And the reason for that is that looking at those confidence intervals, we can tell which colors are different from each other. So we're essentially looking for confidence intervals that overlap and don't overlap. And in this case, just like we could kind of see in the means plot, but you're never for sure how statistically significant those differences are in the means plot. That's why I like the confidence interval plot better, the error bar plot. But again, we can see that blue and white, these intervals overlap each other a lot. So if we're saying, hey, we think the mean is inside these intervals and there's lots of overlap, then those two aren't different from each other. Green seems to be different from both of those, and yellow seems to be different from everybody as well. So what's the moral of the story? If you're going to go into an oat field, don't wear a yellow shirt unless you want to be attracting all of the bugs.